I'll begin the presentation by talking a bit about the technology, because you might not be familiar with it. So it's a facade system that uses glass and water to form an IGU, and the interlayer, which is normally filled with argon or another insulated gas, is replaced by water. This water layer is connected to a mechanical system, usually involving a heat exchanger and a circulation pump. The temperature of the water layer can be controlled as well to optimize the surface temperature of the glass. And as such, water-filled glass can help manage the energy demand of the building through reducing the need for mechanical systems. This is both from the use of the different water temperatures, as I said before, to match demand and the actual performance of the IGU. And it's noteworthy that the usual coatings, such as low E, can also be applied to this technology to enhance the performance further. So in terms of water-filled glass as a product, Water-Filled Glass Limited owns the license to the technology. So it was originally patented by my colleague Matthias as an academic spin-off. He couldn't be here today, so he sends his regards. And the company is still in the startup stage, but it works with various manufacturers and contractors globally to produce different projects. So in terms of how it actually works, it's different to your typical window system. So normally radiation and conduction are responsible for large amounts of energy transfer within the building envelope of a traditional window system. And as we all know, that a lot of energy is lost through your typical facade system, so it's important to optimize these transfers. And to address this, water-filled glass uses the water layer to mainly target this radiative heat transfer. Because water is an excellent conductor of heat and it has a high specific heat capacity, this aspect can be minimized. So in the summer, it helps prevent and delay heat from entering, and in the winter, it minimizes the loss of heat to the outside environment. As I mentioned previously, the heat in this water layer can be collected through a heat exchanger. So a number of studies have been conducted regarding the energy-saving capabilities of the technology. So as shown on the figure, using water-filled glass can provide significant energy savings, and is shown to be about 47 to 72% better than double glass, and 34 to 61% better than triple glass in terms of energy savings. And these studies have been conducted across each major Copenhagen climate region. So in terms of the composition of the technology, the new build applications that use the triple glass IGU, as you can see on the screen, so the water layers on the inside is typically 8 to 14 millimeters thick, and this is both for energy saving reasons and to do with the hydrostatic pressure. The outside layer is just standard argon layer, and the pipework can be hidden within the facade. In terms of retrofit scenarios, the composition is slightly different. It's placed behind the existing facade as a secondary glazing. It avoids the need for scaffolding and changes to the original facade, and it also helps minimize disruption and accommodate an easier install, and it can be attached to the original facade system. Because of these various advantages, many different studies have been conducted. The first group of studies that we can categorize look at the energy savings for a new build scenario with respect to it just being a better performing window. The next set of studies look at water-filled glass that acts as a solar hot water heater. But what's not been checked is whether these energy savings can be optimized to balance the energy demand throughout the building envelope, which is what we've called SEED, so saving energy through energy distribution. So in a typical office building, you've got offices facing all orientations, and whilst each office will have similar set points for the mechanical systems, the local energy demand will be slightly different due to different exposure to solar radiation, and it'll be most prominent for opposing orientations, for example, north and south. And as such, it's possible in some cases that heating may be required for some offices, whilst cooling is required in another at the same time. So this concept is what we aim to consider. Can this heat be moved through the building to help benefit the energy demand in both the cooling and heating required regions? So this is possible through the use of water-filled glass, as the heat can be transferred in the fluid by insulated pipes, which can be put in the floor. So to investigate this concept, a preliminary study was undertaken for 2 cities, London and New York, using Transys, which is a dynamic stimulation software. And since these were both likely to have cooling and heating demand simultaneously, it provided a good indication of the potential of the concept. And we used a shoebox model for a high-rise office building with a high window-to-wall ratio of 90%. In terms of the windows, a base case was also used alongside water-filled glass as a comparison. This will help show the potential for water-filled glass as well as the redistribution potential for a standard window. The base case was a typical double glazing with an argon infill, and the water-filled glass has a 15mm gap with no tinting or low E. It's noteworthy that on the slide, the U value you shown was quite high, but this is a static value. It has a dynamic value, but we'll come on to that. We don't have time to come on to that. The top 2 graphs on each of these following slides show the amount of cooling and heating demand required at each occupied hour during the year. The bottom 2 graphs show represent hours where heating and cooling happen simultaneously between the 2 facades. So as you saw on the previous slide, the north and south, there was a lot of potential at the start and end of the year. So for London, for the east and west, you have not much potential compared to the north and south, but as you can still see, water-filled glass reduces the energy demand considerably compared to double glass. And then for New York, north and south, you'll see there's a lot more potential for seed at the start and the ends of the year. And for east and west, again, there's some potential, but it's not as much as north and south. So in terms of conclusions, in London, if you use water-filled glass instead of double glazing, then we're looking at 58 to 60%, 64% energy savings, and in New York, this went up to 62 to 72%, so this is without the seed concept. And when seed is introduced, you are looking at additional savings of up to about 10% in London, about 12 to 13% in New York. So it can also increase the COP of the circulation pump required for the water layer up to about 19 and 25 for the north and south, 7 and 13 for the east and west. This is expected that if we increase the simulation hours, because it was only done for occupied hours, that the seed concept will show greater potential. Thank you.